Section 7.4, Equations with Rational Expressions. So the steps that we're going to go through are listed on page 247 in your textbook. So I'm not going to actually write them out for you on here, but I highly recommend that you write those into your notes, or at least highlight, star, do something in your textbook so that you remember to do them. So to solve this, we want to figure out what our common denominator would be if we wanted to find one. So in this case, we've got x, 2, and a 4, and then the x's are still here. So our common denominator would actually be 4x. So we want to multiply that to everything. So what that does is we have 4x times 2 over x plus 4x times 1/2 equals 4x times 9 over 4x minus 4x times 1/2 with an x in the denominator. Now notice this x and this x will cancel. We're left with 8. This 4 becomes a 2 when it cancels with that 2. We're left with 2x. The 4x's completely cancel in this case. And in this last one, the x's go and the 2 becomes a 1, 4 becomes a 2. Now this is a lot easier to solve. So that's why you want to find whatever the lowest common denominator is. And when you multiply it to both sides or to everything, you actually get rid of your fractions. Remember back in chapter 2 when we did that, and then we get something that's a lot easier to solve. So x equals negative 1/2. But what you always need to do at the very end is check the number that you got as your solution and make sure that when you plug it back in, you're not going to get 0 in a denominator. So if we look back at all of our denominators here, the only thing that x cannot be is 0. Any other number will not make a denominator 0. We did not get 0 here, so this is our answer. One thing I am going to note is it doesn't matter when you really look at to see what values your denominator can't be. You can do it at the beginning, or you can do it at the end and check the values you got. It doesn't really matter as long as you make sure you check it. So in this case, I'm going to go ahead and just state from the beginning what values x can't be. Notice this is just a 5 and a 10, so those are never going to change. But we have an x minus 2 here. That means that x cannot be positive 2. Because if we made this x a positive 2, this entire denominator would be 0. So we just want to keep that in mind. Now, for a common denominator, 5 goes into 10, so we know 10 is going to be part of it. And this is an entire denominator by itself. So we actually need both pieces, 10 times the x minus 2. So when we write that out, we'll have 10 times x minus 2 times 2/5. And if you want to put these over 1, you can. And then once again, let's pay attention to what is going to cancel out. So notice this 5 can reduce to a 1 and this 10 to a 2. So what we're left with is 2 times x minus 2 times 2. In this next case, those x minus 2's will cancel out, so we're left with 10 times 5. And this last one, these 10's, so we're left with x minus 2 times 29. Now some people can jump straight from here to here, and that's completely fine. Just make sure you show whatever steps you need to make sure you're following and doing all the math correctly. So this first one 2 times 2 is 4 times this x minus 2. I'm just going to go ahead and simplify this down. Distribute it out. And then distribute on this right side. And now we just solve this equation like we did in chapter 2. And so we got x equals 4. Go back to the original. X couldn't be 2, so 4 is okay. That's our answer. Notice this one, we have to first factor this to figure out A, what our variable cannot equal, and B, what our common denominator is. But remember, this is a difference of squares, so we know it's x minus 2, x plus 2. So we know that we can use that now as our common denominator. Also, remember that x cannot be 2 or negative 2, because if x is 2, this is 0. If x is negative 2, this one is 0. And if x is 2 here, this one is 0. So these are the values that we cannot have for our n variables. But we already decided our common denominator is x minus 2, x plus 2. So when we multiply those by 1, we're just with x minus 2, x plus 2 times 1, and x minus 2, x plus 2 times 3 over x minus 2. Once again, if you want to put these over 1, you can. Then we have x minus 2, x plus 2. Notice this first one, nothing divides out, so we can just distribute. And when we distribute, we get x squared minus 4. This next one, these x minus 2's cancel out, so we're left with 3 times x plus 2. And this last one, both of these divide with both of those, so we're just left with minus 12. And since it's quadratic, we have a squared term. We need to get everything on the same side. Factor or use quadratic formula. So we get that x equals 1 or 2. But remember, let's go back and check. Our x cannot be 2, because then it would make the denominator 0. So what we write is that x equals 1, and then you tell me that x equals 2 is extraneous. If you want to just put ext instead of extraneous, that's completely fine with me. But I do need to see both of those numbers, the 2 and the 1. Alright, for this one, notice once again we've got a difference of squares in our denominator. So we know that that's x minus 2, x plus 2. So once again, our x cannot be 2 or negative 2. For the same reason, both of these, either of these would make your denominator 0. And once again, common denominator would be x minus 2, x plus 2. So I'm going to skip a step that I had been showing to let's show you guys what I need to see. So in this first one, notice this x minus 2 would cancel, and this x plus 2 would cancel. So all we're left with on this side is 2x squared. When looking at this one, notice the x plus 2 would cancel with the x plus 2. So we're left with this 3, but we're also left with this x minus 2. And on this last one, this x minus 2 would cancel with this x minus 2. So we're left with this 2x and the x plus 2. Distribute and solve. Remember our two values we couldn't have were 2 and negative 2? We didn't get either, so we're good. So now solving this one, there's no factoring, so we can go straight to figuring out what values x can't be, and in this case, x can't be 6. That's the only number that would make a denominator 0. And our common denominator is x minus 6. So when we distribute it to this first one, notice this x minus 6 would cancel with this one. We're left with 6. This 3 doesn't have anything to divide with that x minus 6, so we're left with the x minus 6. And this last one, the x minus 6 would divide with this x minus 6, so we're left with x. So we got x equals 6, but notice that's the one value that x can't be because it makes the denominator 0. It makes this one and this one in this case. So what we write for our answer is no solution. If you wanted to use that instead, that's fine, but you still need to tell me that you got this and it's extraneous. So now for this one, we're trying to figure out how long it's going to take for the second pipe to fill the pool if it was doing it by itself. So the key thing for all of these work ones is the number of jobs is going to be divided by the time. And I'm using jobs instead of pipes here because we're going to use that to generalize. So let's write out what we know. We know there's a pipe 1, we know there's a pipe 2, and we know there's together. So pipe 1 can fill the pool in 9 hours, so it can do one job in 9 hours. If we use both pipes, the pool can be filled in 3 hours. So that's together. If we use both pipes, they're still doing one job. So this is still a 1. It's one job, one pool, but they can do it in 3 hours. So we're trying to figure out how long it would take the second pipe. So that would be one job over. We don't know how many hours. And for your equation, it's just pipe 1 plus pipe 2. So what pipe 1 can do plus what pipe 2 can do is going to be what they can do together. And with these problems, the setup is the hard part. Once you get the equation, these are easier than the ones we were just doing. So in this case, your common denominator is going to be 9x once you do your multiplying and dividing out. So pipe 2 can fill the pool in 4.5 hours if it was working alone. Alright, so for this one, we're going to start with the general equation of distance equals rate times time. Getting time by itself is distance divided by rate, because notice over here we could divide both sides by the rate. This is going to be important for what we use. The other important thing that we're going to need is time 1 plus time 2 equals our total time, which should make sense. Whatever you do at one speed plus whatever you do at the other speed is going to be what you did total. So how long you were driving for the first chunk plus how long you were driving for the second chunk is how long you were driving altogether. So let's look. So the first one, I travel 120 miles at a set speed. So that, using our formula right here, we've got 120 miles at some speed which we don't know. And then we increase my speed by 10 miles per hour and go 210 miles. So we did 210 and increased whatever speed this was by 10. So it's this r plus 10. It's whatever we were going, which is this r, plus 10 miles an hour faster. And this is our total time, which was 5 hours. So here's our equation. Now we just have to figure out our common denominator, which would be r times r plus 10. In this first one with the red, notice the r here will divide with this r here. So our red is just going to become 120 times r plus 10. Green, the r plus 10s will cancel out. Oops. And so we're just left with 210 times r. And this last one, this 5, doesn't have anything to divide out, so it's just 5r times r plus 10. So we get that r is -4 or 60. So let's go back to our original equation, and we're talking about initial speed. So if we look at our answers, the -4 doesn't make sense because you can't go -4 miles per hour. So the answer is this 60. And on a test, I do expect you to put the units back with it. Tell me which one is the answer and make sure I can tell which one you think is the answer, because it's not both of these. Alright, with variation. When we talk about direct variation, what this means is as one variable is increasing, the other one does too. It's the same thing as if one decreases, the other decreases. This k is what we call the constant of variation. And we'll be seeing this k a lot. The opposite of that would be inverse variation. So as one variable increases, the other decreases. So as one goes up, the other goes down. Or as one goes down, the other goes up. And once again, these k's is still that constant of variation. So the k will be different for each problem, but within each problem, that k is going to be the same. And if that's confusing, we'll get to those. Compound variation is just when you have two or more variables in the relationship, so you're doing multiple variations at the same time. Key thing I want to point out between direct and inverse is notice this one is multiplying. This one has division, or you're dividing. So that's a key thing here. So we're going to start by just going back and forth between words and formulas from those words. So I'm going to try to color code these. So B varies directly. So we know that's B equals some k. Directly is we're multiplying. Fifth power of m, so it's this k times m to the fifth power. So now this next one, r varies inversely. So r varies inversely with d, like that. The other way of writing this one most people find this way easier, but you can do whichever way you like. Alright, so G varies jointly, and it varies with the product of A and B. Product, remember, is multiplying, so A times B. So last one, y varies directly with n. So y varies directly with n, so that's multiplication. Inversely with p, so that's going to be dividing by p. So with these, it helps just to kind of go step by step. Just start writing your equation and decide the multiplication versus division as you get there. And it's always going to be whatever comes first. Something varies directly with, that's going to go by itself on the first side of the equation. So for part A, we want to get a general proportional relationship. So we just want a general relationship without any numbers at all. And that's where we're going to use this second sentence. The amount of drugs needed is directly related to the patient's body weight. So that's just D equals K times W. So now part B would determine the proportionality constant. So we're just going to use the information that they give us to figure out what our K is. So that information comes from this last sentence right here. So instead of D, we found that the person gets 5 milligrams. K is what we don't know, and their weight was 180. So then we just solve this, and we get 136. So now what we're going to do is for C, put this all together. So before we can quite figure this out, let's go back to our original equation here. We know our K is 1 over 36 because we just found that out. And like I said before, within each problem, that K is the same. It's constant. That's why we call it the constant right here. It's always the same number within that problem. So now we want to figure out how much of the drug for if you weighed 234. So how much of the drug if a person weighed 234 pounds? If you want to put this over 1, what you get is 6.5. So how much of the drug? They'd get 6.5 milligrams, because remember we're using milligrams. Alright, so same type of problem. I'm not breaking down the steps for us each time in the instructions, but we're still going to break them down together. So first things first, get our general equation. So the value of the computer varies inversely with its age in months, so I'm going to go ahead and use M. Second up, if the computer is 400 when it's 12 months old. So that's the second piece of information that we're given. So we know the value is 400 when it's 12 months old. We use this to figure out what our constant of proportionality is. Multiply both sides by 12. And now we can put all of this together to figure out what it's actually asking us. So putting that 4,800 in for our constant K. When it's 20 months old, we just change the months to 20. And the value would be $240.